Conservation of energy problems compare states. And because they compare states, generally we're going to be looking at the energy at one state and comparing it to the energy at another state. So in order to do that, you need to be able to figure out and identify different states of the problem. I did that for you already at this one. I asked you how fast it's going at B and how high up started at A. So I created the states for you. In fact, I even went further by giving you information about the state of the problem when the object was at part C. So you have 3 states of the problem clearly identified. Your first step should be to identify what you feel is the reference level for the problem. I'm going to be very clear about it. You'll forget to do this step, and I will be able to trick you because of it. So step 1, consider the reference level of your problem. Now, we started talking about reference level just yesterday, and it was about dealing with potential energy. Reference level represents the lowest place the object could go. So identify where your reference level is and identify that as the lowest place the object could go. Call that 0. So the first thing you need to do is identify your reference level. And all measurements are going to be made compared to the reference level. Now, the reference level could be anywhere. I would encourage it to be the lowest place the object could go. Now, I want you to understand, you don't necessarily know that ahead of time. All right, I want you to be aware that you might have to guess. So that's why you need to make sure you have taken it into account before you begin. The second thing you need to do, identify the states of the problem. They're not always going to be identified for you. So step 2, identify the states of the problem. Where are you comparing the object's energy? Am I going too fast? Or do you already know this so you don't have to write it down? Step 3, list out the possible types of energy an object could have at each step. At each state. We only know about 2 types of energy. So I'm going to list gravitational and kinetic at each state of the problem. This is a reminder for me to go through and try and identify the types of energy that exist. Now, the reason we're doing this is because if we've decided to use conservation of energy, then we're making the bold statement that the energy of the object remains the same. It just changes type. In order to make that statement, we have to make sure there's nothing taking energy away from the system. So we look for things like there's no friction or very low friction. We look for other signs too, that the system conserves energy, like there's no external forces acting on the system except for gravity. Those are things we look for to assume that we can say that the energy is conserved. So after we have placed the available types of energy next to each of the states of the problem, you go state by state and decide whether it has that kind of energy or not. For example, I'm going to start at state C. Why? Because that was where they gave me information. They told me the object was 1 meter above the lowest point. That means it has gravitational potential. Is it above the reference level? If it's above the reference level, it has gravitational potential. So I'm going to go to each of the objects and decide whether it has gravitational potential or not. State B doesn't have gravitational potential. Why? It's at the reference level. Its height is 0. State A, yeah, it has gravitational potential. Why? Because it was started above the reference level. Next, go through and identify the next form of energy. See if it exists at each state of the problem. We know it exists at state C. Why? I'm told it's 2 meters per second. If it's moving, it has kinetic energy. Next, I go to state B. They're asking for how fast it's going. I think that's a clear indication that it's probably got kinetic energy. Also, it's at its lowest point. The only form of energy it could have is kinetic. At A, however, I'm told that it's being released at this point. Probably no kinetic energy there. So we've gone through and evaluated each state for the types of energy that might be present at each state. Your list of energies is going to get longer as the year goes on, but right now we only have a couple. The next thing you do is you just compare the energy at one state to the energy at another. I'm going to compare B and C. At B, I only have kinetic energy. So that's 1/2 mVb squared. At C, I have two kinds of energy. I have gravitational potential. As we learned yesterday, that's mgh. H is 1. It's 1 meter above the lowest point. But I also have kinetic. 1/2 m2 squared. Now that's it. You have successfully used conservation of energy. If it's done correctly, you should be able to get an answer. And looking at this, I think we can get an answer. I know I didn't give you the mass. That's not uncommon. They don't ask you how much you weigh when you get on a roller coaster, do they? So it's likely that if they don't give you the mass probably isn't necessary in the execution of the problem. It seems to me the rest of this is just a little bit of algebra, and not even interesting algebra. Now you just solve for V. Not so terrible. Looks to be like probably close to 5. Thanks. Adam helping me out with my algebra there. So what is the square root of 24? All right, so we went through that pretty straightforward like. Take a minute. I'm going to ask for the answer to A. How high is it? I'll give you about 60 seconds to repeat this process and figure out how high you have to start it. And I'm going to pick on one of you guys to just give me the answer. Picks the wrong word. I'm going to choose somebody I think, needs to speak today. Stop it. I'm sorry, bless you. That's about all the time I think I can afford. So let's see. Kayla, did you figure out how high it gets started? 1.2 meters it is. That's right, 1.2 meters. Does anybody need to see that worked out? Anybody at home need to see it worked out? Pretty straightforward? Yes, sir. Don't think so. In this particular example, you never needed to solve for the mass. The mass canceled out across the board because every term has mass in it. Now, I want to be very clear about this. Do we need to talk about why we got 1.2? Okay. What I want to point out is we were just asked to find things like the height and the velocity, and that we did not need the mass because the mass never played a significant role here, meaning that the inertial mass, which is in kinetic energy, and the gravitational mass, which is in gravitational potential energy, they cancel out here. Now, if I asked for how much energy the object had, you would need the mass. And there are other forms of energy that don't rely on mass. In those circumstances, it won't cancel out. But in this case, it does. So don't be scared if they don't give you the mass. If they don't, it likely means that it's not going to play a significant role in the problem. And in this problem, it doesn't. Okay? But like I said, you can't figure out how much energy there was unless you have the mass. Let's try one for practice again. I'm not convinced that everybody's able to do this, and this will give me a chance to kind of hit up folks at home too and see who's paying attention and who's not. So I'm gonna make this one a little different. Not much different, by the way. But I'm gonna start my little car on this roller coaster at a speed of, say, 1 meter per second. 2 meters above the reference level. There. So I would like to know how fast is the car going when it goes to make the jump? And I would like to know the fastest the car goes. I have two questions. I want to know how fast is the car going when it goes to make this jump? And I would also like to know the fastest the car goes. Everyone understand what I'm asking for? Any questions about what I want you to be able to tell me when you're done? You have two questions. Question one, Vmax. Question two, V jump. So, all right. So I'm going to pick two different people, have them step us through the problem, figure out what they did. One person's going to do the Vmax part. One person's going to do the V jump part. So I'm going to wait for all these folks to kind of tumble back in from being in their breakout rooms. They're taking their sweet time. Here they come. All righty. That's most of them. All right. So let's start with Vmax. I'm going to pick on, how about Aaron? Can you help me out do Vmax?
Yeah.
Excellent. What should I do first?
Okay, so first you want to set up your equation with the gravitational potential energy and the kinetic energy.
Okay, fantastic. Where should I begin with that?
You can start with the gravity and then your reference point to 0.75 to your reference point.
Okay. So help me out. Where do we know the most information about the problem?
Probably at the top.
Okay, so that's state one. And
Right.
where do you think it's traveling the fastest?
I would say at the very bottom.
I think you're right, because that's when all the energy is going to be kinetic. I think we're going to compare those two states. Great. So what kind of energy do I have at A?
So we have both gravitational potential and kinetic.
Perfect. So both of them.
Yeah.
And what kind of energy do we have at B?
No gravitational, just kinetic.
Excellent. So I think that's how we're going to set this up. So help me out here. What do I put for gravitational potential?
So that's your 10 times your reference point minus 0. So I guess just 2.
Okay.
And then, yeah, plus your half v squared because masses cancels.
Right. I'm just going to leave it in there for just a minute because I have some people who are asking questions about that.
Yeah.
So, all right, that's great. So what am I going to set this equal to?
I'm not sure.
That's okay. We want to look at, this is state A of the problem.
Mhm.
So we want to compare it to state B of the problem. What kind of energy do I have at state B?
Oh, so just compare. Okay, so then just do the same thing. So half m times your v squared.
Excellent. That's it.
Vmax squared, yeah.
Effectively, that's all you have to do. You're going to compare the energy at one state with the energy at another. Fantastic job. Now, I mean, yes, you do have to go in the rest of the problem, get yourself an answer here. And this is where you got the 20.5, which is close, but it's not quite done yet. I'm going to cancel all those m's out. And the left side is 20.5, but the right side is 1/2 Vmax squared. So I'll finish it off by solving for Vmax, which means I'm going to take the square root of 41. And that gives you, it's a little over 6. How's that, guys? Not terrible? All right, let's go a little bit further. So Kaylee, can you help us do the jump one?
Sure. So I started by comparing stage, what we want the stage A of the problem.
Okay.
Our final stage becomes the C.
Okay, so we're going to compare state A with state C. Perfect.
So I already had my information about state A. I already knew that side would be 20.5.
Okay, so I'm just going to rewrite all that out because you know me there. All right, so what do I have over on the other side?
And on the other side, it would be, because that side has both gravitational potential and kinetic energy. So it would be,
All right, so we have gravitational and kinetic. I'm just repeating it so they can hear it at home.
the m times 10 times the height, which is 0.5,
Perfect.
plus 1/2 m v squared.
Excellent. There it is. That's it. Once you got that, I think we're pretty well done. You're going to cancel out all the, I mean, there's math to do, sure. But if you can make it to here, you can get the math done. So I feel very confident if you guys are making it to here, yes, the m's are going to cancel. Again, in this case, all the terms have an m in them, so we're okay without it. Now, there might be future problems where that's not going to work out, so don't always assume that that's going to happen, but it does here. And we still have our 20.5 on this side, but now we have 7.5 here plus 1/2 mv squared. So square root of, oh wait, there's no m. I already canceled the m there. So I think this comes out to be the square root of 26, which is just a little bit more than 5. So something like that. Now, if you're able to do these, I think you're going to be okay. Yes, ma'am. That's one of those questions where it sounds like an absolute, and I always get worried about absolutes. But for a roller coaster, yeah. So the question that was asked is the bottom of a roller coaster always where we have our max speed? And like I said, I hate to always make an absolute statement like that because I'm usually proved a liar when I do. But for a roller coaster like this, a simple gravitational roller coaster, yeah, when all the energy is kinetic, you're at your fastest speed. So they have to, you have to have a position where you're at the reference point so you don't have any gravitational potential. And that's what they do here. What's kind of funny is that if you're paying a little bit of attention here, you realize that roller coasters have a limit on how fast they can go. And that limit really is dependent on how high the first lift hill can be. What's kind of funny, I don't know if you guys know this, but in Tampa, they can make the lift hills higher here than they can in other places because we have less restrictions on the height of certain buildings. In Disney World versus Universal Studios, Disney World is in a position where they have a limit to how high they can build their buildings. And the reason isn't because they're not allowed to build them higher. It's because they don't want to put a blinking red light on the top of them. You see, if you make your building above 137 feet, you have to have a red light on it so that planes won't run into it. And so Disney doesn't want to have the Princess Castle with a big blinking red light on it, nor do they want Expedition Everest to have a big blinking red light on it. So all of their buildings come in just under the max. And that's always on purpose to try and suspend your disbelief. Universal Studios tries to do something similar, but they have less of an interest in that because they have a few more thrilling rides. So in order to deal with that, Disney has options, and same with Six Flags. Six Flags has options. They tend to tunnel their roller coasters so that the ground isn't the lowest point. So instead of something like that, you'd have a situation where they would take the hill and take you underneath it. So they could give you an experience where you'd be faster by making the reference level lower than the lowest ground point in the problem. That's particularly common. They also add energy in other ways. Anybody who's ridden Cheetah Hunt knows that you can put energy into the system using other ways, not just a lift hill. So there's options available if you're trying to increase the velocity, but there are limits. Standard roller coasters are limited by the height of their first lift hill. That's where all the energy goes into the system. After that, energy is just being bled away by friction most of the time. Now, if you're capable of doing what we've done so far, I want you to understand that this is not the level I need you to work at. This is below the level I need you to work at. So if you're able to do these, you're looking at the B-C line on your next test. If you want the A-B line on your next test, you have to understand that our tests are cumulative. And because they're cumulative, I have more expectations. And here's one of them. Yesterday, we talked about the scorpion specifically. Well, that's not a great loop, but we're going to stick with it anyways. If you remember way back to when we talked about centripetal motion, which was not all that far back in the Wayback Machine, one of the things we talked about on a roller coaster was that there's an effective minimum speed that you have to maintain, or else you can't be in circular motion. Do you guys remember that conversation? Seems to me like I should be able to combine that idea with a roller coaster and ask you, where do I have to start my roller coaster car in order to successfully make it through the loop and not lose contact with the track? This is a two-part problem. It requires that you remember some things about net force equaling MAC. Use that to figure out what this velocity is, and then use conservation of energy to figure out where to start the cars. So we're going to do this in two parts, but I want you to note that this is the A level. You want to get an A on your test, you got to be able to do problems like this. So let's see if we can't use some of our prior knowledge to do this. We only have a few minutes left before they're going to tell us what's for lunch. So your first job, knowing that the radius of curvature was 0.25 meters, and heck, I'll even tell you that it's a 2-kilogram car, even though you don't need it. I would like you to tell me how fast I have to be traveling so that I do not lose contact with the track. What is the minimum velocity? And since all of you passed that force test, I should be able to pick on any one of you to tell me what this minimum velocity is. And when I say pick on you, yeah, I mean it. So draw your free body diagram, remind yourself which force goes to 0, and find that minimum speed. You've got 2 minutes, because that's all I can afford, 2 minutes. And maybe I'll even put some information here to remind you so you don't have to dive too deep into your notes. All right, just a few more seconds left before I pick out one of you. My 5 people without cameras, they look like targets to me. All right, we're coming up on that 10-second mark. All right, Rylan, can you help me out?
Yeah, so basically the normal force goes to 0. So I did 20 plus 0, which is the normal force, equals m times v squared over r. And the mass is 2, so you plug in 2. And then you don't know the velocity, so you leave that as v. And then it's over 0.25. So then you divide 20 by 2, and then you multiply 10 by 0.25. You get v min squared equals 2.5. Then you take the square root of 2.5 and you get 1.6 meters per second.
Perfect. 1.6 meters per second. That's right. That's exactly how fast we need to be going. If we don't go at least that fast, we will not make the jump. Or not, I'm sorry, not make the loop. So now to figure out the height, your next task is a conservation of energy task. If we accept this as the reference level, you are 0.5 meter above the reference level. Don't make that mistake there. You realize that you are 2 radii above the reference level. People make that mistake. I don't want you to. But once you do that, you realize you've got gravitational potential energy here and you have kinetic. It's your job to figure out where to start the car based on that and that alone. If you start at any less than this, the car won't have enough velocity to make it through the turn. Now, we've done this problem 3 times already today, 4 times really. So I don't see the need to follow this all the way through. I want you to understand that this is my expectation for your test. Because we're getting short on time here, I think you guys can say the gravitational potential energy here has to be equal to the gravitational potential and the kinetic here. That's what I'm going to need you to do. And this isn't the only way this can be done. I want to point out that I could just as easily do it the other way. We could have a track that has a bump in it. And if this was a circular bump, say 0.25, I could do the other version of this problem where there is a maximum speed. If I go any faster than this, I jump off the track. Same kind of problem, test the same kinds of things. But again, this is now finding out what is the max height I can place this without leaving the track. Same kind of problem, still requires a force problem first, and then a conservation of energy problem. Yes, sir. Still didn't need mass for the last problem. Yeah. Yeah. We won't really need mass until we start having forms of energy that aren't based on mass. All right, questions about this part for today. All right, based on this, I want to let you guys know a few things about what I see here in the future. We're not exactly done, but you have homework due Friday. My expectation is that you will submit your work in the morning, and then we'll go through it. But mastering isn't actually required to be submitted until that evening, so that if you get your questions answered, you can go back in and submit for mastering. Some of you have been having issues where you hate the idea that you can't submit mastering before you come to class and get your questions answered. So you need to have your work done and submitted in the morning by 8:30. And then in the evening, you can go back through and finish up any mastering you didn't complete. I'm expecting that we will reach a point where we should have a test by the end of this week. I'm going to put out a practice test Friday for the weekend. We'll go over it on Monday. I'm expecting that if things go well, we'll have a test Tuesday. If things aren't going well, we'll have a test Wednesday. Does that make sense? I would really like to shoot for the test on Monday. I'm sorry, on Tuesday. And I'm going to be very clear as to why. I'm not going to be here Tuesday. So it's an easy day for me to have you guys take a test. If we have to take the test Wednesday, that's fine, but I have to miss Tuesday in the morning, which is going to include your class. So, folks, I'm not done. I'm not sure at what point you thought I was going to finish. I'm done with roller coasters, but I'm not done. Because we have another form of energy we haven't finished. And I want to at least introduce it today. I don't finish until they tell me that we're done, right? Until they say it's time to stand for the pledge. Have you ever known me to just say we're done? Sorry, guys at home, just letting you know. We had a few folks that thought we were packing up, but not even. Because I want to talk to you a little bit about springs. People in physics last year feared springs, but a spring is just an object that tries to retain its shape. There are lots of things that are springs that don't look like a spring. But for us, a spring is any object that, when deformed, attempts to push itself back into its shape. So if you think of a spring like this, if I pull outwards on it and let go, the spring is going to try and retract till it retains its shape. So a rubber band is a spring. You stretch it out, let it go, it tries to come back to retain its shape. An inflated ball is a spring. If you push in on it, it pushes out to try and retain its shape. All of these fall under the category of linear springs, even though they're not all springs. Linear springs experience what's known as a restoring force, a force that attempts to make the object go back to its original shape. That's a restoring force. What makes it linear is that the restoring force is proportional to how far the object has been stretched. What that means is, if I stretch the spring a distance x, the spring looks like this, because it's been stretched out. The spring is going to pull back with a force that is proportional to how far it's been stretched. So mathematics, if I'm speaking my math language, it looks like this. F is force, X is how far the spring has been stretched. K is a special value known as a Hooke's law constant, or the spring constant. The spring constant tells you how stiff the spring is. A slinky has a low spring constant. Doesn't take much to stretch it out. Like a paperclip has a low spring constant. Doesn't take much to stretch it out. The springs on your car, high spring constant. They can take thousands of pounds and only change a little bit of their distance. The spring constant tells you how much your spring will stretch. Now, there's a little bit more to this. These are vectors. force and displacement. Because they're vectors, they have direction. And because they have direction, I have to put a negative sign here. The negative sign is a reminder that the object wants to return to its original shape. So if I push the spring to the right, the force pulls it back to the left. If I push the spring to the left, the force pushes it back to the right. That's what the negative sign means. It means that the force is trying to put the object back where it was. That's what makes it restore. It's a restoring force. It's trying to make the object back the way it was. The reason why we study springs is because you can store energy in them. If I stretch or compress a spring, when I release it, the spring has energy. Bow and arrow, spring. Pinball, spring. Those little wind-up cars you had when you were a kid, spring. They're the easy, simple way of retaining energy. Hooke's law creates something known as elastic potential energy. It's just another form of energy that we have. The thing about elastic potential energy is the energy stored in the spring. It's not stored in the object. The other forms of energy we had, it was really stored in the object. The object has potential energy because it interacts with the earth. Here, the object has potential energy because it interacts with the spring, but the spring holds the energy. That's why you'll notice in our formula for elastic potential energy, there's no mass.
Good morning, St. Louis High School. It's time for the morning announcements. Please stand for the pledge.
Time for the pledge. Pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Thank you. You may be seated.
I will be.
Congratulations to Signals Wrestling. They are 2-0 right now.
Yay, wrestling.
They won last night, 41-21 against.
Do you guys hear these announcements?
2-24.
Then I won't repeat them.
Good job, guys. Congratulations to